Okay, hello everyone and welcome to yet another maths video, and this one will surely be interesting today because we're looking at how to find equations of tangents from a certain point to a certain function. So in this particular example we're going to be looking at a cubic function, the base cubic function, the f of x equals x to the 3. As you can see up on the board there is a rough sketch, and we're considering a point, -2, 0. And what we want to do is we want to find the equation of tangents from that point, and we obviously want them to pass through some point on the cubic there, and that point will be given by a, and a to the power of 3. So as you can see here, we've got the point identified. It does not fit on the cubic model. But then we also have another point on the cubic model, a to a squared, where the tangent actually cuts through. So it's not too difficult in order to solve something like this. It just involves a little bit of thinking about the context and the situation, both geometrically and also mathematically through algebra. So first off, let's start with the f of x, and I'm sorry, that should be a to the 3 there, because of course that's the f of a, which is a to the 3 based on that. We have our f of x, x to the 3. What we need to do is we first need to differentiate it, because of course when we're thinking about the equations of tangents we're always thinking about the slope function, because that's what the derivative is. So when we differentiate it, obviously we just apply the simple power rule and we move the coefficient out to the front and subtract 1 from the exponent. There we go, we've differentiated that polynomial term. And we're all good to go to the next stage. And the next stage is to write this in the form of the f prime of a, because at the moment we just want to focus in on this point a to the 3. So if we write this as the f prime of a, we simply change our independent variable, and we can write it as 3a squared. And that would be the f prime of a. It's always good to think of it in terms of this point just a moment, because of course that point lies on the function. So it's going to be very special in helping us find the answer. So okay, so far been pretty easy. The next step, what we want to do is we want to consider a form to represent or incorporate both of these points into a linear function. Incorporate the information given into a linear function, then obviously solve for values of a, and hence find the equation of the tangent. So in order to do this, we follow quite a straightforward simple form. I'm going to put it in the box here. And if you've studied linear algebra and you've considered points on the Cartesian plane before, then hopefully this should just be relatively straightforward and logical. Essentially what you do is you consider the 2 points and you consider them equal to each other. So what we do is we have the f prime of a, which is what we just found, lot of x, so f prime of a, lots of x, take y, equals, and then we have the f prime of a, lots of a, which of course that's just our x coordinate, and then what we do is we multiply it, subtract, the f of a. And in subtracting the f of a, this is essentially our y coordinate from this special point here, the a to the 3 point. So I know it looks a bit complex, and if you haven't really studied a lot of linear algebra before and you don't understand things like tangents and lines, then you're probably thinking, how does that work? I would definitely recommend having a look at some of the theory behind how this works, but unfortunately I can't go through all of it in this video, otherwise it would be quite a long video indeed. But what we'll do is we'll substitute in the values, because we already know a lot of these values. We know that the f prime of a is 3a squared, lots of x. And we subtract y. We know that the f prime of a is, again, 3a squared. It's a little bit repetitive here. Lots of a. And we know that the f of a is a to the 3. The f of a is simply evaluating a, essentially. Evaluating a at a certain point. So again, a to the 3, obviously, because our f of x is x to the 3. Okay, so now what we can do is we can actually expand this out here. And again, it's quite simple. Well, in fact, we can just really write it without the brackets. That's all we really need to do in terms of expansion, except for here where we actually have 3a squared multiplied by a, and it's probably best to write that as 3a to the 3. Obviously, because we have a squared times a, it's a raised to the power of 2 times a raised to the power of 1, so it's obviously going to be a to the 3, and then we add in the 3 as the coefficient before. Take a to the 3, and of course we can simplify this down even further, just so it's 3a to the 2. 2a to the 3. Silly me. This is what happens when you do maths at 10 o'clock at night. So now what you want to do is you want to incorporate this point that's off the line here. And that's where this a and y idea really comes in handy. So we know that obviously our x-coordinate is -2 and our y-coordinate is 0. So what we're essentially doing here is we're substituting in, because we've got the actual point here. We've got a, which is our x for this point, and we've got y, which is a to the 3 for the other point, but we need to consider the other point on the left-hand side, the one that's not actually on the function. And that's how we sort of construct a linear function. Again, a lot of theory behind it. But what we can do now is we can say, well, okay, we've got 3a squared, lots of -2, because that's our x value. Take 0, because our y value is equal to 0. Not only does it keep things simple, but it works quite nicely. So again, we can write this out as being -6a squared. Again, what I've just done is I've gone -2 times 3, -6, you know that, that's basic, equals 2a to the 3. Again, just rewriting the expression down, but getting rid of that 0, making it nice and concise, because of course that's going to be really helpful in the next step. And what we want to do is we want to get the polynomial all on the same side, so we move 6a squared from one side to the other, and that negative becomes a positive, of course, simple algebra rules. Now, we could evaluate that by factorizing. However, another alternative is to use your calculator, and I will go through the calculator method because it's very handy and it can save a lot of time, because factorizing is very important, yes, but when you're doing a question like this, it's probably best to just use technology where you can, because it's already quite a procedure already happening, and factorizing just adds another layer to that, and again it also adds the potential to make a small error or a small mistake. Relatively straightforward though, not really the potential to make a mistake here, but again, factorizing, especially when you have higher order polynomials, can become quite frustrating. So it's always handy to have a calculator on standby. I've got a TI-84 here, and what we'll actually do is, if the lighting permits, which it semi is we'll go into apps. So the apps key is just this one down here. It's the little purple one. And you want to scroll down to one that says Poly SMLT. Or PLY SMLT, sorry. But essentially what it stands for is a polynomial simulator, or polynomial root simulator. And what you want to do is you want to press on 1, which is Poly Root Finder, in case you haven't seen this app before. If you've seen some of my previous videos, you should have used this. It is a pretty cool tool. But again, you want to select the degree of the polynomial, set it to 3, that's my advice. I've already got it there. If you haven't, just use your arrow keys, it's easy to navigate. Just go across and press enter, or the button down here just to select it. But after pressing next, after sorting all that out, you want to put in your values. So again, we've got 2a to the 3, so the one where it says a3, put in 2. A to the 2 is obviously 6, and we got 0 and 0 for the other two, because we don't have a coefficient in front of a and such forth. Then we press solve, and we've got some values. We've got 0, 0, so it's a repeating root for one of them, but then we've also got -3 as the last one. So it's always good to write up these values of a, because essentially that's what we just found. We found the values of a, so the points on the curve here. And we'll consider them in just a second. I think I just dropped my whiteboard marker, which isn't good. But what we have is we have a equals 3 and a equals 0. Excellent. Well, let's just have a little think about what this actually means. This probably isn't the best diagram representation. In fact, hang on a second. It should be -3, shouldn't it? my bad. Okay, maybe it is a slightly better diagram representation. You can see that, yes, this probably does look like it's x equals -3, because you've got it joining the curve at some point. And then also for the 0 one, again, it's always good to check how logical your answer is. But for the 0 one, what you can do is you can consider that as just being essentially a flat line, because that's what's going to work out in the end. I'll explain that why when we go finding the equation of the tangent. But it does make sense because, of course, it goes through the point, and here, although I've drawn it slightly above the line, there's actually a stationary point on this cubic. And that stationary point is where the slope of the tangent is 0. It is actually a stationary inflection point, because if you have a look at it, it's sort of changing from concaving to convexing, but it's also a stationary point. It's not a point of inflection as you'd normally think of one, for example, on a slightly different looking cubic, where you've probably got a point of inflection there where the slope of the tangent is not equal to 0. But there we go, our answers are somewhat logical, and that's always good because it means that we're probably on the right track. So now what we consider is we think about what this actually means. We go ahead and work out if a equals 3, what would the value of y be at that point? That's essentially the next step. So if a equals 3, obviously we want to find the f of -3, f of -3, and of course what we're going to get from that is we're going to get -3 raised to the power of 3. And in order to do this, we just think of it as -3 times -3 times -3. -3 times -3 is 9 times -3 is -27. So now what we actually have is we have the actual coordinate point of a function on that line. Oh, sorry, actual coordinate point of where that tangent meets the cubic function from that point we were originally given. And what we could also consider is when a equals 0, but I think you'll find the answer is quite easy there, because, of course, if a equals 0, 0 raised to the 3 is 0. So our second coordinate point, the other tangent, would be 0, 0. And they would both go through that point and meet up with our cubic at some position. Okay, so what we do now is we find the equation of the tangent for these two. So when we consider the equation of a tangent, what we have is we have y take the y coordinate. So we have y take -27, and -27, and negative goes to make +27. And then what we have is we have x, and then we have +3, so it must be +3 there, because of course we have negative and a negative making a positive, and it's always take that. Okay, so now what we do is we actually go and set that equal to the derivative of this function, so the slope of the tangent at that point. And again, we found that originally, the f prime of x here, so we go 3 lots of -3 squared, and of course -3 times -3 is 9, times 3 is 27. Essentially, that's what we end up with as the first equation of the tangent. So now what we can do is we can go ahead and actually calculate this and put it into a form of y equals. Again, I just want to check that I have enough board space. We'll be right. So we end up with y equals, and then what we can do is we actually bring up this x plus 3 from the denominator on the left-hand side to the numerator on the right-hand side. So what we essentially end up with is, if I just do it up here quickly, 27 lots of x plus 3, and when we expand that we get 27x plus 81. 27 times 3 is 81, so that's where I got that from. So now, because we have 27x plus 81, we also have y plus 27 on this side. So when we bring it to the other side, it's going to be take 27. So therefore, we need to subtract 27 from 81, and of course we get 54. Again, all you really need to know there is your 27 times tables. So again, 27x plus 54. And there we go. There is our answer. And now, as for the other one, the other equation of the tangent, again, where x is 0 and y is 0, we simply consider, well, I'll just raise it from here. We simply consider this here. The dy dx, of course, will be 0, because 3 lots of 0 squared is 0, so we would just get y plus 0 on x plus 0 equals 0. And I think it's pretty easy to know what the answer to that would be. It's, of course, just going to be 0. And hence, that is the second equation of a tangent. So we found both of the equations of the tangent, again, from that point to some position on the curve. Hopefully you found this video okay. Hopefully you could follow along with it. Again, if you have any questions or comments, please feel free to post them below. I will generally check them as frequently as I can. And again, that's simply how you find it from the point to the actual curve there. So 27x plus 54 is the first tangent, and the other one was just 0, a flat line. Okay, thank you very much. See you later.